Okay, now we're recording. Let's get to chapter 16. Let's finish this guy off. There's two topics to discuss in chapter 16. And they're not particularly hard topics compared to the calculation of pH, but they're still kind of important. As soon as this loads, staring at a black screen. So the first thing we're going to be talking about is the effect of pH active salts. So what does that mean? You got to remember that all of our salts are, if you put in a weak acid into solution, it is going to produce a weak base salt. So if I say dissolve in, say, sodium acetate, you've just created a weak acid salt, a salt that is the conjugate base of a weak acid. And so that's going to actually affect the pH, even though you don't always realize it. So even though we don't really necessarily have an acidic proton or a hydroxyl group, some salts will affect the pH because they're conjugate pairs. If I mix ammonium chloride, you're going to see like reactions like ammonium breaks down and it acts as an acid to form ammonia. If I use sodium hypochlorite, besides being bleach and bleaching the shit out of your clothes, it's going to accept a proton because this is a weak base. So even though this does not have an OH, when I put bleach, it's going to produce some hydroxide. Now, even cations that we don't really think of with conjugate acids, like iron and aluminum and chromium and copper and zinc and cadmium, can undergo hydrolysis. So when iron dissolves in water, iron forms this iron hexaaqua complex, much like the iron thyrocyanate. But this iron hexaaqua, hexa meaning 6, can then donate a proton. So this hexaaqua can form a pentaaqua hydroxo complex. So some of these metals can act as acids. And thus, when you mix the iron chloride into solution, you suddenly have a slightly acidic solution. If I mix aluminum chloride and it dissolves, you'd have a slightly acidic solution for the same reason. And so, how do we deal with this? Now, in general, when we look at pH active salts, we can place these in 4 different scenarios. 1, both are pH active, or is like neither are pH active, or one of them is pH active. So how do you think about this? So you want to, when you see a salt and you mix it into solution and you're wondering, is a solution acidic, basic, or neutral? You split it into its cation or anion pair. And here's where you have to think about strong acids, strong bases. A neutral salt, the conjugate acid of the basic salt, or the conjugate base of the acidic salt, would make a strong acid or a strong base. So sodium is a neutral salt because if you add a hydroxyl onto sodium, you get sodium hydroxide. Sodium hydroxide is a strong base. If I have chlorine, if I add a protein to chlorine, I have hydrochloric acid. Hydrochloric acid is a strong acid. So a strong acid will make a neutral salt. Strong acid will make a neutral salt. So we have to put a hydrogen and see, does this look like one of our few strong acids? Does this look like one of our few strong bases? If we can do that, that means, oh, it's not going to affect pH. So sodium chloride, not going to affect pH. Potassium iodide, not going to affect pH. But if I say sodium bicarbonate, well, bicarbonate comes from carbonic acid. Carbonic acid is a weak acid. So bicarbonate will act as a base. And so it will affect the pH. So now acidic salts. So acidic salt, if it's going to be a salt, it's either going to be the cation is a metal, one of those stated metals, or the conjugate acid of a weak base. So iron, but it could be ammonia. So to make an acid, you look to the cation. To make an acid, you look to the cation. To make a base, you look to the anion. So for a basic salt, a salt that's going to affect the base, you look to the anion. You see acetate. Acetate is the conjugate base of a weak acid. Sulfate is the conjugate base of not H2SO4, but HSO4. HSO4 is a weak acid. LiF, F is a weak acid. HF is a weak acid. If you're wondering whether a salt will affect the pH, you look first, what is the cation? Is the cation one of these special metals or the conjugate base, the conjugate acid of a weak base? Is it basic? We look at the anion. Is it the conjugate base of a weak acid? Now, we will probably not do the fourth type. The salt is mixed capabilities, where cation is acidic and the anion is basic, because then you have to look at the size of the Kas. So that's a pain in the ass, and no one wants to have to deal with that. But you could hypothetically deal with that. If I said iron acetate, you'd look at what is the acidic strength of iron, what is the basic strength of acetate, and say which one is stronger. We're not gonna. We're gonna save ourselves the headache. But, okay. So how to do this in practice? So as I said, we look at our salt, we split it into cation and anion pair. You add hydroxide to the cation until it's neutral. There's only 8 strong bases. So if it doesn't look like one of the 8 strong bases, then it's pH active. Add protons to the anion. Does it look like one of the 9 strong acids? No, then it's pH active. If the answer to both these are no, then we have to compare the two. So, okay. So let's look at this. Predict whether these salts would be acidic or basic in solution. So we have nickel chloride. So I break this down, I'm going to have nickel 2 plus and 2 Cl1 minus. If I put hydroxide onto nickel, does NiOH2 look like anything we've seen as a strong base? And hopefully you're going to say no. Our strong bases are only in group 1 and group 2. So our sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, barium dihydroxide, strontium dihydroxide, and maybe calcium dihydroxide. So nickel dihydroxide is not. So nickel would be acidic. Now chloride. If I add an H onto chloride, it forms HCl. HCl is a strong acid. So Cl minus is not pH active. Cesium iodide. As I said, split it to cesium and iodine. Cesium, if you put cesium OH, cesium hydroxide, that is a strong base. That is not pH active. Iodide, if you have H to it, it's hydroiodic acid, which is a strong
How
acid.
do how do you know which one to add? Like, how do you know when to add the hydrogen and when do you add
You
the
always add
other?
the hydrogen to the anion. You always add the hydroxide to the cation. You always
Can you repeat that, please?
add the hydrogen to the anion because you want the plus to match with the minus, the H plus to match with the anion's minus. And you always add the hydroxide to the cation because you want the OH's minus to cancel the cation's plus. So like you want it to cross over. So the OH minus goes with the plus, the H plus goes with the minus. And if you look at that, does this look like one of our strong acids? Does this look like one of our strong bases? Is the question you need to ask yourself. And
So if they're both acids,
if they're
then it
both
would
strong acids, then if they're one's a strong acid and one's a strong base, then it is neutral.
okay.
Because remember, a strong acid completely deprotonates. A strong base completely dehydroxylates. So if they completely go to the product side, there is no reverse reaction. Basically, what you're looking at here is, will a reverse reaction occur that it goes back to some of the acid? You're adding products and you're saying, will the reaction shift back to the left and form some of our acid or form some of our base? If it doesn't, then our reaction is done and it is neutral. Now let's look at this guy. This guy's a pain. This guy, you can only look, you've never seen this guy before in your life. So more likely than not, that guy's going to be acidic. That guy looks like none of the bases. That would be trimethylamine. So no, that guy is definitely not one of our strong bases. So there's no way in hell that's going to be anything but acidic. Now phosphate. You add a hydrogen to phosphate, you have HPO4 2-. That is definitely not a strong acid. So you have a acidic cation and a basic anion. The question becomes, which one of these is stronger? And I'm not going to ask that of you right now. And this last one, barium iodate. Oh, hypoiodite. Barium hypoiodite. If you add hydroxide to barium, you get barium dihydroxide, which is a strong base. Iodite, if I add hydrogen hypoiodous acid, which is a weak acid. So this guy is going to be basic. You have to kind of have a little flashcard of what of our strong acids, what of our strong bases. Come test time, since we're going to be having a freaking take home anyways, I think there's not very much of a choice at this point. You're home. Yeah, so you can have those weak
So I have a question.
Yes.
For the third one, the really long, are we just supposed to assume that it's an acid or not? Because I'm still kind of confused on that one.
Okay, so this whole thing from the CH3 3NH, all that is the cation. All that is the cation.
Okay.
So, because it's paired up with PO4, because it's paired up with PO4, that's the anion. It'd be PO4 3-, and this guy's going to be 1+. So, I'm gonna actually stop the screen share so I can draw what this would look like real quick. Share. Well, I could go to whiteboard. So what this guy looks like, if there's N, and this is how this would look without the hydrogen. There's the CH3, CH3, CH3. And what we've done is just like hydronium, this is our water. Just like hydronium, we took one of those lone pairs and made another bond. Make the plus. We're going to take this lone pair and make a hydrogen bond, which is going to give that nitrogen the plus. So that's what we're actually looking at right there. I know that's a hot mess, but if you can break it down into what the anion is, then it becomes what is the cation. The cation is everything the anion is not. Okay.
So if one is
So as far as it being an acid or a salt or a base, what would it be considered?
This would be this one. Let me click the next thing so you can see acid, salt. This one, without the Ka and Kb information, we can't know. And for a test, I'm probably not going to ask that. But you would say, how big is the acidity of this guy? How big is the basicity of that guy? And you say, the stronger one wins. The stronger Ka, the bigger Ka wins. But we can't do it with that one.
so
here's-
for the Ni and Cl2. So
because
if one's base and one's acidic, well, that's just neutral, right?
yes, but okay, you got to remember which one is a strong acid, which one is a strong base. The strong acid guys will not go back. Strong base guys will not go back. The weak acid or weak base will reverse.
So if you have two, you just look at which one's stronger.
Yes.
But if they're both strong, then it's just neutral.
Yes. Okay, so here's our first clicker question. So for anyone who's actually on clicker, should be able to do this, real life, real time. I'm asking you guys, identify which salt would form a base in solution. Which salt would form a base in solution? As you're thinking about this, so remember, you break it down into cation, anion, pair. The cation is responsible for acidity. Anion is responsible for basicity. You got to think which one of these guys would make this all basic. How many participants do I have? 23 participants. That's pretty good. I will remind you
How
that.
do we answer this?
How? Do you have clicker?
Yeah. It's just being weird. Oh, I see it. Never mind. I just had to scroll down.
So yeah, you just need a, yeah. So for those who haven't used clicker before, yeah, you should, when you log into the class and whatnot, the poll should send you the screen if you're, so even if you're not paying attention and you just log in, for example, you just log in and you're not watching live stream, you should still get these questions. I hope, if I'm doing this right. And then you can like answer this. And Olivia, I just wanted to let you know I got your message. Whatever response you guys do, I'm gonna, I guess, count it for both of you. So no pressure. And a reminder that until I get this sorted out, in about 4 or 5 minutes, I'm gonna close out this meeting and start the second meeting. I should be able to get this sorted out by Friday, where we can have just one 50-minute meeting. but I don't think
I
it was.
thought we did that. We did that
They
Monday.
gave us a gift. They gave we're feeling generous. Here, we'll remove the time limit if you like
Oh.
upgrade. And now I actually need to like fill out the paperwork that says, yes, I'm a school affected by COVID. Please extend our time limit. So that's why. So it was not a normal. I mean, maybe it'll let me do it again, but I don't want to wait too long and then get caught with my trousers down here where they're like, oh, you're out of time. So I'd rather just get it at 10:25, start the class back up, and start at 10:30. Okay. I'll give you another 30 seconds for those who are there to maybe finish up. I have no clue how many people are actually on Clicker right now. I'm not looking. So made it to 4:15. Hopefully keeping hydrated, not running out of paper towels. Okay. So now for that one, correct answer was, let's see, D, duodenum. Na is a strong acid. NO3 is from, well, sorry, Na is from NaOH, strong base. NO3 is from strong acid, HNO3.
So wait,
So you want to look at for a basic salt, we want to look at the anion. HNO3 is a strong acid. HCl is a strong acid. HCl is a strong acid. HBr is a strong acid. Only acetate comes from acetic acid. That's the only weak acid on there. So D would have given you a base. C would have given you an acid. A, B, and E would all give you salts. A, B, and E would all give you salts.
how would it give you salts? I'm just trying to make sure I figure this out.
When you put HNO3 into solution, it forms NO3 minus, and it's not going to go backwards.
So when you break it apart, since NO3 is your it's a negative, so it's your
Anion, yeah.
anion, you got to add your H to it.
Mm-hmm.
And then you said that's a strong acid. And then Na is a +1, so you have to add the OH.
And that's a strong base.
The strong. Oh, okay.
And so because they're both strong acid and strong base, they both cancel each other out.
I got it now. Thank you.
Okay. Now, it's 10:25. I'm going to go ahead and stop this meeting real quick, and I will immediately start recording. Okay.
Mom, make some margarita.
Yeah. Okay, thank you. Recording. So there's several things that are going to affect the acid strength. That what makes a strong acid, what makes a weak acid, a weak acid. Some of them are easy to see, some of them a little harder to see. The first one is bond electronegativity. Bond electronegativity. The better ability to pull the electrons from the proton, the stronger the acid is. The better ability to pull the electrons from the proton, the stronger the acid is. So HCl is highly negative. It's able to pull electrons away, so it becomes very acidic. H2O, it's a little bit weak. It's a little bit weaker, but we all know H2O can act as an acid. NH3 N is weaker, less electronegative than oxygen. So it's definitely not an acid. It's usually a base. Now the other thing is bond strength. The weaker the overall bond, the easier it is to break. So if the bond is too strong, we cannot completely ionize. So even if it's electronegative, if you cannot remove the can't break the bond, you cannot become strong acid. So even though HF is the most electronegative of all the H acids, it actually has a really strong bond strength, which makes it weaker. So HI is highly electronegative, but it has a really weak bond. So HI is a stronger acid than HBr, which is a stronger acid than HCl, which is a stronger acid than HF. So bond electronegativity is a big thing, but also bond strength. But one of the things that you should be able to see and be able to pull out, even if you don't remember your electronegativity trends, is the stability of the conjugate base. The more stable the anion, the easier it is to form an acid. So, what do you think? Ethanol ethanol is not typically an acid because it forms a naked oxygen when you have a CH3, CH2O, H, and you lose that O. Now you use that H. But acetic acid is a very similar structure. The only difference is it has a C double bond O. And because it has a C double bond O, we can do what's called a resonance structure. That's going to shift the charge and stabilize this guy. That many oxo acids and organic acids, if they have these nearby double bond O's, can stabilize these structures and make them stable. That essentially, like, if you look, HNO3, really strong acid. We didn't really talk about this, but HNO2, weak acid. H2SO4, strong acid. H2SO3, weak acid. H2CO3 is a weak acid, but it's still an acid. HClO4, strong acid, because when you lose the proton, there's 4 possible resonance structures. We can move that negative charge here, here, or here. But if I look at HClO3, I'm trying to move this so we can, HClO3, it's a weaker acid because you can only move the charge to 2 places, 2 different places. So there's only 3 resonance structures. And if I said HClO2, you'd only have 2 places. So it's a weaker acid still. HClO, there's only 1 possible place to put the charge. So it's the weakest of all the ClO acids. So these multiple oxygens, the things that made these guys a bitch to name, were the things that are going to make these guys strong acids, because you can move that charge to any of these oxygens.
So the more resonant structures, the stronger the acid is?
Typically. So you may, this is acetic acid. This is acetic acid. You may say, well, that's a weak acid, Andrew. But it is an acid. This is an acid because you could draw this, which is the CH3CH, so a CH3 CO2 minus. You could also flip the double bond down there and the oxygen up there. If I remove this oxygen, this would become ethanol, and ethanol is not an acid at all. So taking off this oxygen turns this from an acid to neutral. So even though this is a weak acid, it's still stronger than a non-acid. So whenever you have a lot of oxygens, they typically become stronger acids. Now there's a few exceptions, as I said, like H3PO4, that's a weak acid. H2CO3, a weak acid. But those aren't too bad. The last topic is Lewis acids. Lewis acids and Lewis bases are just one more extension on the acid-base theory. That it's just a different way to think of acids and bases. Bronsted-Lowry acids and bases, we looked at acid as something that loses a proton, base is something that gains a proton. Now, when we go to Lewis acid and bases, we look at it not as the proton, but as the electrons. So that a Lewis acid is something that accepts electrons, and a Lewis base is something that donates electrons. The same thing happens. We're just flipping who we care about. And this allows us to think of metals as acids and other things as bases that we wouldn't normally think of as bases. No longer do we have to worry about protons. No longer do we have to worry about protons. I'm going to jump back a few slides just to show you that when we talked about these, we talked about, well, iron is an acid. We talked about, well, iron, aluminum, chromium, copper, zinc, cadmium, all acids. Well, they're not acids under Bronsted-Lowry definitions, but they are acids under Lewis acid definitions. Because what do? They accept electrons because they are missing electrons. Basically, they are hungry for electrons, and so they attack the electrons to get them. They are hungry for electrons, and so Lewis acids need electrons. Now, before we get all super confused, remember, protons are still Lewis acids. Because a proton, it has no electrons. What does it need? An electron. Where is it going to get it? From the base. OH minus. What the hell is those minus? That minus is the electrons. When it donates those electrons to make water, it's acting as a Lewis base. So all this means is we're changing how we're thinking of this so that we can deal with our like a little bit bigger things. HCl still donates a proton because protons are deficient of electrons. But now we no longer need an acid. BH3 is a Lewis acid, and it's not going to donate any protons. BH3, what do we know about boron? We know boron is group 3 metal. Group 3 means it only has 3 electrons, which means that when it makes 3 bonds with hydrogen, it only has 6. Back in last semester, we talked about the octet rule. Boron is 6 electrons. It's one of the exceptions. It does not have an octet. So what would it want to do? It needs 2 electrons to make an octet. So it's going to want to bind with something with 2 electrons to make an octet. Now, OH minus still counts as a base, but now OH minus can attack anything, not just hydrogens. For those who have to take organic in a semester or so, Lewis acid and Lewis base is something you really want to understand because you'll hear words like electrophiles and nucleophiles. Nucleophile is just a fancy way of saying a Lewis base. Electrophile is just a fancy way of saying a Lewis acid. Electrophile is something that likes electrons. Nucleophile is something negative that likes to attack a positive nucleus. So BH3 can be attacked by ammonia to form this adduct, this Lewis adduct that's held together by coordinate covalent bonds. The Lewis structure, the equilibrium lab that we just did, or a lot of you guys are just doing, all the iron is attracted to the iron is attracted to the Lewis. The iron is attracted to the thiocyanate. The thiocyanate is a Lewis acid, Lewis base attraction that we're going to see. Okay, so we're going to get into this. We're going to start looking at these. Remind you guys, I posted some problems worked out on YouTube. So if you have struggling on some of the problems on chapter 16, or you started to look at chapter 17, I got some of those already worked out up on YouTube. But throw some problems out. So this one, we're going to look at buffers, we're going to look at titrations, and we're probably not going to go as much into titrations as they do go in here. I might actually throw some homework problems out. I'm sorry for those who have already done them. I'll probably still throw them out because they're a pain in the butt, and I'm trying to shave some of the time off of the class of what we're covering. But so, the idea here, we start with the common ion effect. The idea that in an acidic or basic pH, we typically only thought about what if we only had reactants. That if I only have acid or I only have base, what's the pH? But now we have to think about what if we add some of the base to the acid? What will this do to the dissociation? Well, Le Chatelier's principle said if we add products, the reaction will shift towards reactants, away from the products. So if we can say there is almost no or very little hydronium or hydroxide in solution, some dissociation must still occur, but less will occur if we have some conjugate base in with the acid, or we have some conjugate acids in with the base. And this is the concept of buffers. I'm going to kind of skip through this. There's some math. You can look at this math at your own time. But basically said, if I calculate my HF, what's the pH of just 1 molar HF? And we do it like we would have normally done. We say blah, blah, blah. The concentration of acid would be 0.026. There's our Ka. Here's our setup here. Now, what happens if we add 6.3 grams of sodium fluoride and say, so 6.3 grams, if we calculate turn that grams to moles, then in liters, moles divided by 1 liter, that's 0.15 molar. So we've added this into this term. So what's happened? So instead of the concentration being 0.026 for acid, it's now 0.0045. So we've lost by factor of like 4, something like lost by a factor of 4, something like that. Concentration of acid has gone down. Now, if you get to the point where they're nearly equal, the amount of HF and the amount of NaF are the same, we end up seeing that the concentration is dropped even more till get to the point where the concentration of H plus is equal to the Ka. As if this is 1 molar and this is 1 molar, 1 molar and 1 molar cancel out, and we get the Ka is equal to the H plus concentration. So if I have equal amounts of acid and conjugate base, that becomes as simple as we can. But so the main thing we're going to talk about in this chapter is a buffer. A buffer is a solution that is a mixture of a weak acid and a conjugate base. It has to be a weak acid or a weak base. And it has to be the exact conjugate. You cannot make this with, say, acetic acid and sodium fluoride. Sodium fluoride goes with HF. Acetic acid goes with sodium acetate. If you start mixing stuff together incorrectly, it's not going to make a buffer. It's going to be all kinds of weird. So you could make this out of ammonia and ammonium chloride, because that's a weak base and a conjugate acid. You can make this out of acetic acid and sodium acetate. It doesn't matter. But a buffer is made where you have weak acid and conjugate base, and it's going to be resistant to the change because of this. Now, buffers are really important for you people who like biology. You want a buffer because it keeps your shit alive. Enzymes thrive in buffers because enzymes need certain pHs to stay active. Proteins need certain pHs to stay active. If suddenly you have like spicy taco night, and suddenly all your enzymes die and you keel over dead, that's kind of problematic. You need something where you get a little bit too much acid or a little bit too much base, you don't keel over dead. You want something that's going to withstand a little bit of change. And that's why our buffers. If you have something, you take, you eat some food and suddenly your stomach like wildly changes in pH and you can't digest food, you're going to have some problems. You're going to have, that's why your stomach acid is buffered. It's going to keep it from changing too drastically. Blood is buffered. Even seawater is buffered to some extent. So the fish isn't going to die if you accidentally pour some acid down the drain. A little bit too much rain and like a little too much acid rain, and suddenly the entire economy of Japan is shot, you know? Something like that, you know?
Good riddance.
Thank you. Well, that went dark. So. Now, how does a buffer actually work? Because you have both weak acid and conjugate base, if you add any straight up base, your weak acid will neutralize it and make more conjugate acid. If you add any acid, straight up acid to your conjugate, to the buffer, the conjugate base will neutralize it and make more weak acid. So as long as we have enough weak acid or enough conjugate base, it will keep neutralizing OH or H+, and it'll keep the pH more or less the same with very little change. You get a very slight change to pH, but not nearly as large as a pH change as you would if you had no buffer. So as long as the weak acid and conjugate base remain, the pH will stay buffered. If we add too much hydronium or too much hydroxide, we will break the buffer and we will see a large jump in pH for that reason. So as soon as the OH minus is greater than the HA, suddenly we see a huge change, because suddenly that last drop of OH means we have naked OH. That last drop of hydronium means we have naked hydronium, and suddenly the pH is dependent on the hydronium, not on the weak acid. So our equation is still this. Our equation is still this when we calculate this. The only difference is now only the H plus is unknown. We will know the A minus, we will know the HA. So we can actually make this a little bit easier. So what I've done here is we multiply HA to both sides, we divide by A minus to both sides, so H plus is by itself. And then if you take the negative log of both sides and separate everything, we get pH equals pKa plus log A minus over HA. This is known as the Henderson-Hasselbalch equation. It's basically the equation to easily look at buffers. This is usually known. The pKa is known. And the only thing that's going to vary for your equation is how much A minus and how much HA do we have. That stuff will be known. If you do that, you can find what is the pH of your buffer. Now, when we make a buffer, we need some amount of weak acid and some amount of conjugate base. Then if they are equal, pH equals pKa. Now, quick reminder, what is pKa? pKa, if pH is the negative log of H plus, pKa is the negative log of Ka. So it's just a convenient way to look at our Ka. When we dissolve this, we make a buffer, we dissolve the acid with the conjugate base salt, and it'll make that buffer, or the base with the conjugate acid salt. But in general, this is a hard, fast rule. Buffer is only good about plus or minus 1 pH unit away from the pKa. So if your pKa is 5, you will not be able to make a buffer that is 7. with that setup. You can make one that is 5.5. You can make one that is 4.3, but you're not going to be making something 3.8 very good. Why? Because this is a log-based scale. Log-based scale means every time to get a change of 1, you have to have one of these numbers 10 times greater than the other. If you want a change of 2, you have to have one of these numbers 100 times greater than the other. And if that's the case, if you have one of these numbers 100 times greater than the other, then the buffer is only going to work real good in one direction, not like the band. So make a buffer. The desired pH will always determine which buffering agents you should select. We'll select the buffering agents based on what is the pH we want. We'll do this clicker question, and this will probably be where we end for the day. So identify the combination that will result in a buffer solution. So which of these guys will we combine to actually make a buffer, regardless of what pH it is? Which of these guys can we mix together to make a buffer? Sorry for those of you who missed out or whatever. I said hopefully by next class we will have this sorted out. It will be just one straight shot. And I'll delete all the other meetings we won't need. Remember, we need weak acid, conjugate base. Don't overthink it. Nope. It's my alarm telling me finishing up. So after this. So 15. I'll give you guys to 2:30, and then so 30 more seconds. Stop the poll. So I don't know how many people are clickering. So 16, 10 seconds. Gotta guess. No pressure. And we're stopped. Okay, so for a buffer, you need a weak acid and its conjugate base. So HCN is not a strong acid. It's the only non-strong acid. So there's strong acid in water. No, not the right mix. This guy is a salt and sodium. You got the right sodium, but that is a strong base. Will not make a good buffer. This will technically make some sort of buffer, a little bit. You'll make but if you have equal amounts, you're just going to neutralize that, and it's not going to actually make a buffer. If you have a bunch of ammonia and a little bit of strong acid, you could make a buffer. But only this one is the correct pair of CN minus and CN minus of H and K. Okay, so that's where we're stopping for today. And we'll pick up where we left off on Friday.